Guys, we talked about this for 10 minutes, then we talked about this board over here for 10 minutes, and then I realized I might have videotaped a cell phone number, which is, probably not a great idea. So, I'll review the tape. If we actually didn't get the number in place, I'll put the video up, but otherwise, I don't really want to dox you guys, That would not be friendly. Okay, so don't dox your friends. Where was I? So we have this wonderful formula for the length of a vector. Let's look at an example, because this example will lead us to new ideas. All right, so if I have vector A equal to, we'll keep it 3D here for a second, 1, 2, 3, right? And if I look at A dotted with 1, 0, 0, what happens? If I look at A dotted with 0, 1, 0, what happens? If I look at A dotted with 0, 0, 1, what happens? How does the formula work out? We do what? First times the first, second times the second, third times the third component, and add them together. So what's that look like for us here? Right, yeah. So exactly 1, 2, and 3, right? Now, if you want, let me just put out the gory details here. What happened? We had 1 times 1 plus 2 times 0 plus 3 times 0. That's the man behind the curtain here. That's the using of the formula, right? X times x, y times y, z times z. Add them together. That's the dot product. So in this case, we get 1, 2, and 3. What does this show us? This shows us something. Actually, this is equal to what? This is equal to, in retrospect, A dot x hat, A dot y hat, A dot z hat. See, because this is exactly x hat, this is y hat, this is z hat, right? You remember that? So I'll remind you, x hat is equal to 1, 0, 0. In many of the other standard works, it's either an I or an I hat. Now, if it's I, it's not really I, it's a bold-faced I, right? Not bold-faced lie, bold-faced I. So, but I prefer x hat for reasons that will become more clear as the semester goes on. This is a more physics or engineering notation. The reason for I, and this one either is y hat or j, z hat or k, it actually is historical. Back in the 19th century, there's a dude named Hamilton, and he was working on extending complex multiplication to 3 dimensions. He finally figured out that he had to go to 4 dimensions. So he took a real number plus scalar multiple of I, scalar multiple of j, scalar multiple of k, and these are called quaternions. In quaternions, you use IJK notation, all right? And that was the dominant formalism in mathematical physics engineering for maybe 1840 to 1900. And then we discovered the vector formalism, which is easier. And it's pretty much just taken over since then. Now, there are still people who adhere to the quaternionic formalism. It has certain advantages in terms of coding, graphics, and things like that, which I don't fully understand. The way quaternion math works is weird. And the people who like it have almost sort of a religious devotion to it, honestly. But anyway, we use vectors, but in honor of Hamilton, that's why the IJK notation is there. I just don't care that much about Hamilton. I prefer a notation which is more explicit about what it's about. X hat is a vector which is of length 1 in the x direction. Y hat is a vector of length 1 in the y direction. Z hat is a vector of length 1 in the z direction. What do you think theta hat's going to mean later in this course? It's going to be a vector of length 1 in the theta direction. What would that be? Like that angle, right? What's the theta direction? It's like curving around, right? In the direction which theta is increasing is what that's going to mean. So anyway. Okay, so look, the point of this is we can calculate components with dot products, right? So we have another theorem, if you like, which is that, well, let me not write down theorem. I did want to get to your homework problem, so let's go on. Now, this brings me to a definition. Well, before I get to a definition, let me state a problem, example 2. All right, so I'll do it kind of generically, but suppose you've got a vector, oh, that's where I'm going to get into trouble. My apologies in advance if I've exchanged the roles of A and B as the way I introduced it in the notes. It doesn't really matter. You could go either way. But let's see. Suppose this is the B vector, all right? And then down here I've got the A vector, all right? My question is, what part of A is in the B direction, if that makes sense? Maybe I need another idea here. Maybe it's not time for this yet. I may be getting ahead of myself at the moment, but you can kind of visualize it, right? Like there's a shadow of B onto the A direction. So if I drop this like perpendicular, right, then there's a particular vector down here I'd like to talk about. This is what I would call the projection of B onto A. All right. Now it turns out that there's a formula for that, and the formula is simply this. And here's the notation for it. Projection of, so I put the direction down here, A, of B is equal to, well, B dot A hat in the A hat direction. See, that's already going on in example 1, right? In example 1, I've got my vector A, right? If I drop down here into the xy plane, see, this right here, well, I guess I could draw it here, right? This would be what? This is A3z hat, right? Which we could also write as A dot z hat in the z hat direction, right? And if you take that and you move it back to the z axis, or if you could think about it here if you want. I mean, but the unit vector in the z direction, of course, points up like this, right? So the projection of that vector onto the z-axis is given by this right here. This is exactly the projection in the z-hat direction of A. So generalizing that notion from the coordinate directions to just an arbitrary vector direction A, we have this formula by analogy. If I can do it for x hat, y hat, z hat, I can do it for A. The A-axis, if you like, just the same. This is the vector component of B in the direction of A. All right? The vector component of B in the direction of A, or the projection of B onto A. How would you get the scalar component of B in the A direction? What do? It's very simple.
You drop the A hat?
Exactly, just drop the A hat. Precisely. What if you want a formula for this that doesn't use the unit vector? What would you do? It's pretty simple. What is A hat? It's what? You guys told me it's A over A, right? And using properties of the dot product, we can pull that 1 over A squared out. And then we've got B dot A, right? Or, of course, you could write that as B dot A over A dot A. Now, I think I lost something, didn't I? Well, what did I have here? I had an A, right? See that A? I can't just ignore it. It's still there. Right, so this is a number multiplied by that vector, this number multiplied by that vector. Again, the projection is a vector. The thing in parentheses is called the component. I mean, I don't often use this notation, but this thing in parentheses right here is the component in the A direction of B, all right? So I ask you some questions about that in the homework. That's how you calculate it, all right? Now, I just used a word in passing, perpendicular. What does that even mean? I think you have a notion of what perpendicular means in 2 dimensions for sure, right? 2 lines meet are perpendicular if they have what? Negative reciprocal slopes, right? One line has slope 2, the other one has slope -1/2. They're perpendicular, right? But the other way. What about 3 dimensions? How would you define perpendicular? What does it mean for two vector directions to be perpendicular? Anybody?
Would it be something with like one having 0 in some direction and another having 0 in a different direction?
So you're thinking about example 1 as like a prototype for what's going on? So you're like, I know intuitively that x hat, y hat, and z hat are examples of perpendicular vectors. That's like a really solid way to think about this. All right? I like that. I like that a lot. Whatever we mean by perpendicular, surely x hat, y hat, and z hat are mutually perpendicular, right? I think that's a great observation, which I'm trying to find a spot to write in. So, observation. X hat, y hat, z hat are perpendicular. I totally agree with that. Like, that's just geometrically clear. You can focus your attention on the plane in which any pair of those exists, and in that plane they have negative reciprocal slopes in the sense of one's a horizontal line, one's a vertical line, right? So like infinity is -1/0. Don't tell the other math professors. I'm just joking. There is a systematic and logical way to use infinity. We're just scared to do it in the calculus classes because there's some nuances there. How should we categorize this idea with dot products? What can you notice about the dot product of x and y hat, x and z hat? What do you see? What's the dot product of any 2 of these with the other? I mean, any one of them with the other?
It's always 0.
It's always 0, right? And so, since there's really no loss in generality of thinking of arbitrary vectors, you can think about if you think about 2 vectors, if they're perpendicular, right, you could set up a coordinate system where the x goes in the one vector direction and the y goes in the other vector direction, right? So surely it's reasonable then to expect that a dot b being 0 should be our meaning of perpendicular in general. And that's in fact our definition. So, I'll put it right here, definition. A perpendicular to b if a dot b is equal to 0. All right? Great. So I was claiming that this dotted character right here, right? B, 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 this, I said, is perpendicular, right? Let me draw this picture. Let me blow this up over here. It'll be okay. It'll be okay. Anytime I erase a board, I had some thought. I'm going to refer to this later. I already referred to it. We're okay. We can go on. They cleaned the board with water. I can see the streaks on it. That's why if you use an eraser on the clean board, it like streaks everywhere because the water on the board catches the junk in the inferior non-shirt based eraser. Let's see here. So I want to talk about the orthogonal projection. Okay, so I'll make it bigger. What did I have? The upper vector was B, and this one was A, right? And I'm after, so I described to you already that on the bottom we have the shadow, if you will, the projection of B onto A, this down here, right? So this right here is projection in the A direction of B. The blue, I have notation for it. I don't think it's just me, but it's not, I mean, you're not going to find this in Stewart, I don't think. You won't find a lot of things in Stewart. You know why? Because it was written by a mathematician, and mathematicians don't actually know Calculus 3 because they've never actually lived Calculus 3. They haven't been a physics major. They haven't come to terms with what vector calculus actually does to the real world. I have. That's why my Calculus 3 feels fundamentally different than what you'll see in Stewart. Because I care about how we actually use Calculus 3, not just what is nice and easy for students to understand. So, not that I'm trying to make it like more difficult than it is. I really am not. Okay, so that should be the perpendicular, like that, we call that orth, and I'm saying that should be perpendicular to this, right? Now I'm making a claim that you can find a perpendicular vector like that. Can you guys tell me the formula for orth? We learned vector addition last time, right? If you believe in vector addition, what formula must be true for projection and orth? Yeah? Oh, no, you're jumping the gun. What, so how about, oh, you're right, but how about this? Would you agree? What Sam said was right, but it was not the, it was not the answer I was looking for. Because I was looking for something dumber. Well, not really dumber, just more, everyone understands why I write that, right? Because this vector plus that vector is B. It's the tip-to-tail vector addition. And then we get what Sam just said to me, which is that orth must be what? Orth of A of B must be equal to what? B minus the projection onto A of B. All right? And there you go. That's the definition of the orth. And I have a feeling I might have assigned you a homework problem to prove, right? It's a straightforward exercise to prove, and I won't do this because we have other things to do today, but you can easily check that the orth A of B dotted with the projection onto A of B, guess what? That's equal to 0. So that's a claim which you can check, okay? Now rather than checking that claim, let me invest some of our time in working an example. All right, so I want to talk about, I want to find the distance to a point, from a point to a line through a given pair of points, all right? And I'm going to show you how we can use this projection idea to do it. Oh, see what I'm saying? My bad. All right. All right, so I need to make sure I've already worked one homework problem today. I shouldn't work another. So example, I mean not entirely, example 3. All right, let's suppose we've got a line that goes through the point -1 to 8. And the other point it goes through is 3, 4, 5. There, it's awful enough. And so statistically speaking, there's a 0% chance I can pick a point on the line. But in my lecture, it could happen. So let's hope that doesn't happen. If that happens, this whole example blows up in my face. But I'm just going to put this point over here, and I'm going to judge it to be, and this is just totally me making something up, but let's do 4, 0, 1. Hopefully that's not on this line. Okay? What's a line? I'm assuming you have some kind of understanding of what a line is, right? But we will define a line algebraically in here in a future lecture. Until then, we're going to think about it geometrically and use vectors. So the question, in one of your questions in the homework, like problem 2C, is to find the distance from a point to a given line. What does that mean?
The shortest distance?
Right, so like what would the distance from me to the class be? So it comes down to the question, are you closer? Or is he closer? Or is he closer? You're closest, right? So however far I am from you to me, that's how far I am from the class. So when we have an extended object, the length is defined to be the length of the closest constituent of the object to the point in question. What is the question there?
So wouldn't it be a perpendicular line?
Yes, yes, and so that's the essential point here, and you can see that, right? You can see that because if you were to bend the line one way or the other, that would be a longer line, right? Now, again, I'm using geometric intuition there. We could probably prove it. Let me not do that. So, okay, great. How do I use projections to get on this? So what I'm really, so let me introduce some vectors here. What are the vectors you want to think about to solve this problem? How about this? I make this right up here the A direction, right? I make this here the B direction. Then the point I'm interested in right here would be what? P should be equal to A plus the projection onto A of B, whatever that is. That would give me the closest point. See what I'm doing? I'm starting at the point I know, which I'm given, namely minus 1, 2, 8. And I'm adding a vector displacement to that point. This right here, right? This is the projection onto A of the B direction up here. So if I take this point plus that vector, it gets me right to where I want to be. Let's actually calculate it, yeah? So what's A? Minus 1, 2, 8, right? So I'm just identifying A as a vector from the origin, just the point in the vector. I'm making that identification. If you want, I could add an axis to here, like an origin, and draw this all based on an origin, but we don't need to do that. We can think about this picture as I've drawn it. So we have this plus what? Now, in this context, since I don't really care about A hat, I might as well use the slick formula which doesn't use the unit vector, right? Which would be what? So I'm supposed to do, remember it was this formula over here? B dot A over A dot A. So let me just write it out symbolically. A dot B over A dot A in the A direction. How's that go? Minus 1, 2, 8 plus, let's see here, A dot B was, what is A dot B? That's a good question. Now what is B though? We need another idea for B. So you might think B is just 401, you'd be wrong, right? That's not what B is. B is the directed line segment from minus 1, 2, 8 to 401. If I call this, let me call this point just to give it a name, Bob. Oh, that's a bad idea. Q. And we'll call this point over here R, right? Notice that the vector B is, what we want really is the QR vector, right? Which we have a formula for. It's R minus Q. Right, so what is R minus Q then? So we've got, 4, 0, 1, minus 1, 2, 8. That works out to 5, minus 2, minus 7, I believe. So there we've got our b vector, we've got our a vector. Do we have our a vector? Oh, we don't have our a vector either, do we? What is the a vector? Oh, wait a minute, I said a was minus 1, 2, 8. Oh, I'm an idiot. Is a minus 1, 2, 8? You guys should stop me there. Come on, guys. Don't let me sell you that. The natives are restless. All right. So I shouldn't say that, right? That's not A. What is A? If I call this, so this is, I said this point was Q. Let's give this guy a name. What do you want to call it? Pac-Man. There we go. So A is the directed line segment from what? From Q to Pac-Man. Also known as Pac-Man minus Q, right? Which is what? 3 minus 1 is 4. 3 minus a minus 1 is 4. 4 minus 2 is 2. 5 minus 8 is minus 3, right? So in fact, we've got 4, 2, minus 3, plus what? What's A dot B? We've got 5 times 4, right? Plus minus 2 times 2, plus minus 7 times minus 3. So what is A dot B equal to? I got 45, but I think that's because I added 4 rather than subtracting it. 45 minus 8 is 37. 37? Yep. 37. What's A dot A? See it? 16 plus 4 plus 9, right? A dot A is what? $29, right? And then A, well, we know what that was. That was 4 minus 4, 2 rather. 4, 2 minus 3. And then you add them together, and that gives you the point on the line, which is closest to that point. Now, does that answer the question? How far? What's the distance from the point to the line? It does not, right? So then, how do you answer the question actually? Yeah, the distance would be equal to, I called this point R, right? So it would be simply the magnitude of the vector that you get from R minus P, right? You just calculate the length of the line segment that goes from the closest point that you found to the point which you were given off the line. That is one way to solve problem 2C, which I think is straightforward. A straightforward application of the ideas that we talked about today. And this shows you why the ideas we talked about today are powerful, because it's just solved the problem you guys couldn't crack with raw geometry with a method. Yeah.
How did we determine that that is A hat plus all that stuff?
How do we determine what?
Yeah, like you have A hat plus
there's no A hat here though, but there's no A hat. Which one?
A vector. Sorry.
A vector.
Yeah, that.
This?
Yeah, that one. How did we get there?
Geometrically. So like this point here is A. I mean, this point here is, oh, curses. Ah. Yes, you're right. So what should I have there? You know, pride goeth before the fall, right? What was my fall? My fall was saying, I don't need to draw the origin. Dummy. Apparently I did. See, because if I'd drawn the origin, it might have been clearer to me that what I'm thinking about is slightly wrong, because really to get to this point P, I'm going to this point, right? Which is what? Which is what I've called Q, right? So really I should have Q vector plus that. So it shouldn't be A here, it should be what? It should be Q, right? So sorry. So I hope this is making you guys feel better. Let's see here. So I should put that there, right? I think have we chased all our demons down now? I think we've got it now. So assuming I haven't looked past something obvious, that's how you do that problem. All right. All right. So let's look at something interesting. Oh. Let's apply this dot product idea to an arbitrary pair of vectors, and let's try to borrow from trigonometry. So what do you guys know about trigonometry? Anything? Let me draw a picture. No, you know nothing? I refuse to accept that answer. Okay, so if this is A, right, and this is B, right, and this is theta, which is an angle between A and B, what could you draw here? I mean, I'm kind of begging the question. I certainly could put this right here, right? And if I make it a vector like that, what vector would go here? I'll call it C. What would C be equal to? Yeah, so you can, I always look at it this way. A plus C equals to B, so you're like C is equal to B minus A. Agreed. All right. Huh. Can you guys tell me anything you know about this triangle? What if I just like redraw the triangle over here like this, get rid of the vector nonsense, just put a theta here. This is length A, this is length B, this is length C. How are A, B, and C related?
Law of cosine.
Law of cosines, very good. So you know that C squared is equal to A squared plus B squared minus 2AB cosine of theta, right? Maybe you forgot it, but this is the law of cosines. If you were in my Calculus 1, which is impossible since I haven't taught it in like 10 years, you would have proved the law of cosines in your first homework. That is how I roll. Now, C squared, check this out though, C squared is C dot C, right? We learned this today. The dot product is the magnitude squared. The dot product of a vector with itself is the magnitude of the vector squared. But we can also look at as B minus A dotted with B minus A, right? And then we can use properties of dot products to multiply this out, distributive property, all that jazz. So what you got is you got yourself a B dot B minus B dot A minus A dot B plus A dot A. But we can simplify this, right? B dot B is B squared. A dot A is A squared. So lo and behold, we've got, A squared plus B squared minus 2A dot B, right? Conform. Agree. That's why you're in college, to prove you can conform, right? You can jump through a set of pre-assigned tasks Prove yourself to conform? No? Isn't that the point of college? Or is it to think? I don't know. The debate's not done on that, I guess. College is job training, right? We all think of our majors in terms of our jobs rather than what we want to understand. It's kind of sad. Anyway, so how about this? C squared is C squared. So what does that mean? These must be equal. Theorem. A dot B is equal to AB cosine of the angle between the vectors. That formula I just boxed is logically equivalent to the law of cosines. However, it's so much better than that because we can talk about vectors in n dimensions, and this formula is still legit. All right? Why is this formula important? Because it allows you to calculate the angle between vectors by dot product and magnitudes. So let me ask you a question that I always ask. And if you're in my physics class, you're not allowed to answer this. But let's suppose we have a cube, like so. It's supposed to be a cube. I know it doesn't quite look like that, but so here's a cube. So like this point, let's make it a unit cube. So that point would be 0, 0, 1. This point down here would be, for example, 1, 1, 0. All right? And the question I'm going to ask you guys is, what's the angle, if we go back in here, all right? So maybe what's the angle between the vector which comes from the origin out to this point, right? What's the angle between that vector, which we call that vector A, and the vector which is vertically in the direction up from the back here along the z-axis like that? What's the angle between A and B? Again, if you're in my physics class, you're not allowed to answer this. But how about anybody else? Want to guess? 45 degrees. Thank you. I appreciate your answer. It's perfect. What's that?
I'm forgetting what it is.
Pi over 4. Yep. Or in grads, 100, I guess. No, wait a minute, 50? Anyway, but I, being, my grandfather told me never trust people, only trust Jesus. That's good advice to live by. No offense, but I don't trust you. So let's see, is it actually 45 degrees? How would we judge it? Well, we just need formulas for A and B. So how about this? A would be, so this point out here would be 1, 1, 1, right? So A would be 1, 1, 1 minus the origin. So we don't actually, subtracting the origin is kind of an easy calculation, right? And then how about vector B? It's, it's 0, 0, 1. So actually vector B is z hat, isn't it? All right, great. So what's A dot B? A dot B is 1, right? So yeah, I'll write it out more excitingly. 0 plus 0 plus 1. So yeah, like you said, 1. What's the magnitude of A? What's the magnitude of B?
Square root of 3.
Square root of 3 and 1, right? So the theorem we just found, law of cosines, says what? It says A dot B is equal to AB cosine of the angle between them, right? Or we could solve this more elegantly for theta is equal to the inverse cosine of A dot B over AB. This is a formula worth knowing, right? By the way, something I have not emphasized enough today, but you should understand, some of these formulas I've written are just utter nonsense if you have a vector which is 0, right? What's the unit vector in the direction of 0? I can't say. What's the angle between any vector and the 0 vector? I can't say. because these formulas break down in that case, right? You could say it's nothing. You could say it's everything. I guess it depends on glass full, glass empty. I don't know. But so here we have inverse cosine of apparently 1 divided by the square root of 3. What is that equal to? I think it's about 54.7 degrees. So if you're in my physics last semester and you remember things, you'll be amused by this because, of course, what did I also get physics to say? 45 degrees, yeah. Someone always says 45 degrees. It's like, because that's what you want to think, right? Because I draw the picture in enough of a garbage way that you can't see that the angles, you don't have any, it's not a good perspective of the vectors, right? Because if you could really see the perspective of the vectors, you'd realize it's not a square that they lie in, but a rectangle. So the length of this is 1, but the length from here to here is actually like, well, square root of 3 apparently. So that they're not equal lengths in the right triangle that you're finding the angle. But I think that's much easier to discover with vectors than it is the other, any other way. Everybody who's here already done the sheet? Just checking. All right. No? Oh, okay. I still need a top hat, right? Oh, yes, 2 times. Although I've was talking to Professor. Just do all 75 feet over. Yeah, I know. Well, Professor Dromby was saying we don't have to sync it to the canvas, so it matters even less that I do it actually. But listen, I want to show you guys something. So listen, in a perfect world, we'd spend 20 hours a week doing calculus, and because like there's no other way I'm going to get people to sit and listen to me talk about calculus for 20 hours. Oh, don't worry, this is just complex. Where was I? Somewhere in here. No, that's not what I want. What? It was already open? Ah! Well, that's annoying. We were added at the start. After all of that, a minute ago, I was already on this PDF. Like, duh. All right, so listen, I'm working my way through chapter 1. What I've just done with you guys is an improvement of what's in the notes for sure. I think the notes are pretty good for the most part. There's a few typos here and there. I wanted to talk about some of these. Oh, yeah, let's see here, where was I? Top hat. Where are we? What class is this? Physics 230. No, we don't want that. Well, this is embarrassing. Yeah. The contrast between this and theory of the dot product, it's clear to me. Whatever. Fine. All right, there we go, finally. 9836, are you? Again, I'm sorry to even waste our time doing this, but I have now satisfied the university requirement, yay. Again, I'm actually taking attendance with the paper, just to be clear. Can I go back to my PDF, please? Yeah. Right. So we proved a few of these today, right? We proved a few of these today already, right? Oh, thank you. And so I think, who knows, there might already even be a solution to your homework in my notes if you look, right? It's totally possible. If you're stuck, the other thing to look at would be the solutions to the problems from 2014 that are posted. There's like, I assigned 20 problems rather than your 15, so there's actually more solved there if you look. What? Seriously? Really? Wow. Thank you. But there are deeper things about vector length and the dot product I should mention to you that would take me another class period to prove. But since you're not all math majors, I won't prove them. But I do need to tell you about them because they're important to know about. Actually, this one would be very easy to prove, that if you have the length of a vector times a number, the length of the vector times a number is just the magnitude of the number, the absolute value of it, times the length of the vector. That makes a lot of sense, right? If you take a vector and multiply it by minus 13, the length of minus 13 times a vector is just 13 times the length of the vector you're multiplying by minus 13. I mean, that's just very natural. The other thing is the triangle inequality. If you have the sum of two vectors, the length of the sum of two vectors is less than or equal to the sum of their lengths. You'd actually get equality when what? When the vectors are in the same direction, right? When they're collinear, actually parallel. We'll talk more about that tomorrow, all right? Tomorrow we're talking about the cross product, which will be sort of the natural completion of our discussion of angles between vectors. It answers some other questions we haven't even addressed yet today. The Cauchy-Schwarz inequality, it relates the magnitude of the dot product to the product of the magnitudes. This actually justifies the existence of the cosine over there from one perspective. So anyway, these are deeper properties, and the proof of them is actually kind of nuanced. Like, it would take me 20 minutes of careful argument to get those here, okay? They're not simple, but the proofs that I give here work in n dimensions. Here's the definition of a unit vector. We talked about that before. Let's see here. So that's what I started class with. The other thing I just wanted to show you a picture of. All right. Oh, we just did that example, right? But with 1 instead of alpha. Oh, 54.74. Wait, did I say? What did I say? Yeah. Don't ask me my children's birthdays, but I remember that. I remember my children's birthdays. Of course I do. You can't prove otherwise. You can't derive children's birthdays, though, you know? It's a problem. It's a problem. That's the other thing. It's like I'm teaching Sunday school to the high school class at my church, and it's really hard. Like, you can't just derive it. You have to like read the words and stuff and like really try to understand what they mean. And there's like some really deep disagreements about the meaning too, that people have just glossed over. And when you try to teach it, all of a sudden you become aware, oh man. All right, anyway, what I wanted to show you was these pictures just briefly. We can also talk about the distance from a point to a plane, right? And again, it should be the distance to the closest point on the plane. And if you really think about the formulas that I've told you about today with projection, if you can pick a point on the plane, and you can pick another point on the plane, then you can use the vector lying in the plane and the vector that points from one of those points to the point off the plane, and you can play games with the projection to find the point on the plane, which is the shadow of the point off that plane. And then you can find the distance from that shadow point to the point off the plane to find distance to a plane. All right. Now you don't need all that when you're talking about planes that are parallel to the xy, xz, or yz directions, right? Because you can just see it. You can just see that 235 is closest to the point 230, right? And the distance from that point to the xy plane is just 5, right? We don't need any kind of fancy vector formalism for that. Or that this is length 3 from the yz plane. Or that's length, let's see here, length 2, I think, from the xz plane, right? Am I saying that right? No, that's 3 from the xz plane. That's what? 2 from the yz plane. It's the one you're not using that's determining the distance, right? The distance from the xy plane to that point is determined by the z component. It's funny the way that is. By the way, so I think that's pretty much, come on, stupid double scrolling. I've covered the lion's share of what I have to say about the dot product in the notes. The end of this section, for those of you who are more motivated by physics and so forth, I have a laundry list of what does the dot product do in physics. And just to read them off to you, you can use the dot product to define kinetic energy, because the kinetic energy is based on the speed squared, which is v dot v, right? The velocity dot the force is the power of the force, the power that the force develops. And then you have these other examples from like second semester physics. The most basic thing, of course, is that the dot product of a force with a displacement gives you the work done by the force if the force is constant. We'll come back to that later when we talk about how to calculate work done by a non-constant force over a curve, but that's much later. Anyway, so tomorrow, cross products. And hopefully I'll talk about the equations for lines and planes as well.